Algebra 2, 9.3, trigonometric functions of any angle. In section 9.3, our objective will be to evaluate trigonometric functions of any angle and find and use reference angles to evaluate trig functions. Okay. Basically, in this section, what we're going to be doing is we're going to be combining section 9.1, our SOHCAHTOA or right triangle trigonometric definitions, with our 9.2, which means that now we can have angles bigger than 180 degrees, and we can also give angles in terms of radians instead of degrees. So we're going to be combining those two ideas. So we're actually going to come up with a different definition for our trig functions. Our original trig functions were in terms of the opposite and adjacent side of a right triangle. Hey, those won't work in this case because we're going to be finding sine, cosine, tangent of angles bigger than 90 degrees. So obtuse, even bigger than 180, bigger than 360, we know that angles can be positive. Bigger than 360, we know angles can be negative. Okay, and so we need a way of finding the sine, cosine, and tangent of those angles. So these are our new definitions. So we're going to let theta be an angle in standard position, and we're going to have x, y be an ordered pair, a point where the terminal side, okay, the terminal side of that angle, okay, intersects the circle. So we have a circle of the form x squared plus y squared equals r. So this is a circle centered at the origin. Okay, its center is 0, 0, and a radius of r. Okay, so this has a center. So this circle here has a center of 0, 0. And a radius of r. R is the radius. Okay, so if we have this, so basically we just have an angle. We have our initial side and our terminal side, just like we had before. We have our initial side here and our terminal side over there. But then what happens is our terminal side intersects the circle at this point here, at this point xy. Okay, and this circle has a radius of r. We can actually now define our sine and cosine and tangent in terms of that ordered pair, and in terms of that ordered pair, x, y, and the radius. Okay, so the sine of that angle, if you notice my angle here, in this case is an obtuse angle. So I can't use SOHCAHTOA because it's not, I can't make a right triangle out of an obtuse angle. Okay, so the sine, now our new definition for sine is going to be the y coordinate of that point, so this y coordinate over here, divided by the radius of that circle. So it's a ratio of the y coordinate and the radius. So then cosecant still is the reciprocal of that. So it would be the radius divided by the y coordinate. Okay. Cosine would be the x coordinate divided by the radius. Okay. And so secant would be the radius divided by the x coordinate. Okay. And then tangent would be the y coordinate divided by the x coordinate. Okay. But then of course your x coordinate can't be 0 because you can't divide by 0. And cotangent is your x coordinate divided by your y coordinate. Again, here y can't be 0. Okay. Okay. And where these come from, it's not magic. It actually comes from this right triangle. Actually, let's give that a different color. It's actually created from this right triangle here. Because that x coordinate, this x coordinate is actually corresponds to that side right there. Okay. And the y coordinate, this y coordinate corresponds to how high up we are. There's my y. Okay, and my r there really is my hypotenuse. And if we think of, so really it's coming from that SOHCAHTOA idea. We just can't use SOHCAHTOA because we don't have a right triangle with the angle theta in it. With that angle theta in it. Okay. All right, so we sometimes call these functions circular functions. Okay, so they're sometimes called the trig functions, which that's what we've been using them as, trig functions. But because of this general definition, we call them circular functions. Okay, so now we can use this new definition to find the sine, cosine, and tangent. Okay, so here we have let -4, 3 be a point on the terminal side. So we basically know our x and our y. Okay. On the terminal side of an angle theta in standard position, evaluate the 6 trig functions. So if we use these definitions from over here, we're really going to need to know our radius. We don't know that yet. So step 1, find the radius. Okay, so I need to find the radius. Find r. Okay, now how do we find it? Again, r is the distance from the center, from this center here to this point on the circle. So it's really that distance right there. There's a couple different ways you can do it. You can do a distance formula. This is the point 0, 0. This is the point negative 4, 3. You could use the distance formula. Hey, subtract the x's, subtract the y's, n squared, and use the distance formula, back from geometry. You could also use, another way of doing it, is use our Pythagorean theorem. If we zoom in here, we can see we basically have a right triangle here, who, since this x coordinate is negative 4, I know this distance here is 4. Since my y coordinate is 3, I know this distance here is 3, so I can go 3 squared plus 4 squared, use my Pythagorean theorem, 3 squared plus 4 squared equals my radius squared, and I could find it that way. So this is actually a triple. My radius ends up being 5. So now that I know my radius, I can find all my angles. So we have the sine of theta. Well, we know the sine of theta is equal to y over r, so my y is 3, my r is 5, so sine theta is 3/5. So since sine theta is 3/5, then we can find cosecant theta would be 5/3. Okay, cosine theta is x over r. My x is negative 4. My radius is 5. So now we can actually have negative ratios, negative cosines. Okay. So then secant theta, again, is just the reciprocal of that, negative 5 over 4. And then tangent theta is equal to y over x, so 3 over negative 4, so negative 3/4. So then cotangent theta would be negative 4/3. Okay, so there are our 6 trig functions. We found it using our x over our y over r, x over r, y over x definitions. And to help me keep them straight, little rule of thumb. Alphabetically, think of alphabetical order. Alphabetically, cosine C comes before S, X comes before Y. So I know cosine is X, sine is Y. Okay. And then tangent, I like to think of as rise over run, Y over X's. Basically, tangent's kind of that slope idea. Okay, the ratio of the Y's to the X's. Okay, the unit circle. We talk about the unit circle a lot in pre-calc. Here's an introduction to it. Basically, what the unit circle is, it's a circle with a radius of 1. So this is the equation for it. X squared plus y squared equals 1. So it's basically a circle with a center 0, 0 and a radius equal to 1. Okay, this one's super useful because then our definitions, we love the unit circle because then my y over r definition now becomes y over 1, which is just y. So if I'm on the unit circle, the sine of theta is just equal to that y coordinate, and the cosine of theta is just equal to the x coordinate. Again, only when that radius is 1. That's why we like it. And we like this one a lot when dealing with what we call the quadrantal angles. Okay, that's a big fancy word for basically the quadrantal angles or any of the angles that end up on one of the axes. A quadrantal angle has a terminal side is on an axis. Okay, so basically, if you're dealing with degree, the quadrantal angle is any multiple of 90 degrees. 90 degrees are any multiple, 90, 180, 270, dot, dot, dot. If you're in radian, it's any multiple of pi over 2. So pi over 2, pi, 3 pi over 2, dot, dot, dot. So in example 2, we're going to use the unit circle to evaluate the 6 trig functions of 270 degrees. So first we need to figure out where the heck is 270 degrees. Well, 270 degrees, well, there's 90, there's 180 to this point. So then 270 is going to go all the way around to there. So 270 is going to be this negative y-axis. Well, I know the ordered pair of that point. It's going to be left and right 0, down 1, negative 1. So since I know it's 0, -1, I know the x and y, and this is a unit circle, it's got a radius of 1, I can just use these definitions from up here. So I know then that the sine of 270, the sine of 270 degrees is just going to be that y coordinate, -1. So then the cosecant of 270 degrees is going to be the reciprocal of that, which is also -1. Okay, the cosine of 270 degrees is going to be the x coordinate, which is 0. Okay, the secant of 270 degrees is going to be the reciprocal, 1 over 0, which that one is undefined. And if you take your calculator and try to find the secant of 270, it says domain. You can't do it. Okay, the tangent of 270 degrees then would just be, again, still the y over the x. So my y, -1 over x, which is 0. Oh, can't divide by 0. That's undefined as well. But I can find the cotangent of 270, because if I flip it, I get 0 over -1, which that's just 0. So the cotangent of 270 degrees is 0. So there's the 6 trig functions. Reference angle relationships. Okay, so we need to talk about something called a reference angle. And you'll see in the next example, in the next set of examples, how it's useful. Okay, but first I'm going to help you find the reference angle. So if theta is an angle in standard position, so I'm just going to go ahead and I'm going to draw an angle in standard position. So I'm going to put it over here in quadrant, I think, quadrant 2. Okay, so there's my theta. There's my theta right there. Okay. The reference angle for theta is the acute angle. We call this theta prime. We would read that as theta prime for the reference angle. It's the acute angle. So acute, that means it has to be less than 90, or pi over 2 if we're in radian, formed by the terminal side of theta and the x-axis. So we're always looking for the acute angle made between here and here, which would be this angle here. This is my theta prime. Okay, so there is my reference angle. My reference angle is that angle right there. Okay, so that's if it's in quadrant 2. Okay, if it's in quadrant 1, that's a pretty simple case, because then if theta is this angle here, theta prime is also that same angle. Theta prime is also that angle right there as well, because it's that acute angle. So we don't really do reference angles if we're in the first quadrant. Okay, if we're in the third quadrant, okay, let's draw theta in third quadrant like that. It would be this angle here. Okay, then theta prime would be this angle right here. Again, it always has to be acute, and it always has to be the angle that's created with the x-axis. So if there's theta, theta prime's that little angle there. And if we're in the fourth quadrant, okay, let's go ahead and let's put an angle in the fourth quadrant down here. So positive angle would be this angle here. Okay, the reference angle would be this one right there. There's my theta prime. Okay, so if this big angle is my theta, there's my theta prime. And really what we use these reference angles for is to help us find the sine, cosine, and tangent of any angle. We relate it back to the reference angle because then we can create, we like using that reference angle because then we can create a right triangle out of it. Okay, like here we can create a right triangle out of it, and that can help us find the coordinates for that xy. Okay, that's kind of our end goal. Oh, we can't really see that xy down there. Okay, next, so we're going to practice finding reference angle in both radians and degrees. Yay, radians! All right, so we want to find the reference angle for 5 pi over 3. Okay, so where the heck is 5 pi over 3? Okay, so first I need to figure out where that is. All right, first of all, we know, okay, here's 0, over here would be pi. Okay, so if I'm in thirds, 3 pi over 3 is 1 full rotation. Okay, so then what would half of that be? I would have to divide by 2, so that would be, this is pi over 2, we know that one. So I can't get that to thirds, but I can get it to 6. So if I multiply by 3, that would give me 3 pi over 6. So 3 pi over 6 is straight up like that. So then 5 pi over 6, well, if that's 5 pi over 3, and here I'm just getting common denominators, guys, that's all I'm doing right now. So if we have 3 pi over 6, that's in terms of 6's. So I'm going to write this in terms of 6's. So multiply by 2, just to figure out where that's at. So this will give me 10 pi over 6. Okay. So if 3 pi over 6 is a 90, then 6 pi over 6 would be a 180. So then that's 1, 2, 3 pi over 6, 4, 5, 6 pi over 6, 9 pi over 6 would be down here. I'm just going up by 3 each time, noticing that pattern as we go. Okay. So then 10 pi over 6 would be a little bit more. So 10 pi over 6 is going to be like right here. So that's going to be this rotation. And we know 10 pi over 6 is the same as 5 pi over 3. So that's going to be my theta. So here's my theta. So my reference angle is going to be this angle here. Okay, but how do I find that? Okay, that's the tricky part. Okay, well here, if we notice, this is actually just shy. This one is just how much less than a full rotation am I? Okay, so we know a full rotation in radians is 2 pi. If you don't know that right now, you need to practice that a little bit. A full rotation is 2 pi. And we're actually back 10 pi over 6 from that. Okay, so to find what that little theta prime is, I'm going to need to take my full rotation, which is 2 pi, and take off that 5 pi over 3 to figure out what that little piece there is. Well, we need a common denominator, times 3 times 3. So this would be 6 pi over 3 minus 5 pi over 3. Which means that 6 pi over 3 minus 5 pi over 3 is 1 pi over 3. So there's my reference angle. So that's a nice little acute angle. I know this angle right here is pi over 3. And we don't worry about rotation. Reference angle is always positive. Okay, so we're pi over 3. Right. So now we need a reference angle for negative 130 degrees. Okay, so for negative 130, so negative 130 degrees. Okay, first of all, we're rotating in negative direction. So here's negative 180. We don't want to go that far. Okay, so not that far. Okay, negative 90. So to go in negative 130, it looks like we're going to be somewhere, I don't know, 50 degrees short. So there's rotating that direction. There's my negative 130 degrees. Okay, so that's my theta. So to find my reference angle, my theta prime would be this angle right here. So basically I'm looking for all the way around from here to here would be negative 180. So meaning how much farther do I have to go? If I'm negative 130 already, if I want to get to negative 180, I'm going to have to find my reference angle here. I'm going to need to take my 180 and subtract that 130 to figure out how many degrees is left, which would be 50 degrees. So my theta prime is 50 degrees in this case. That's my reference angle. Okay. All right, how we use this, okay, is to actually evaluate trig functions. So here's our steps. We're going to go do 3 steps, and we're going to do it for both a degree angle and a radian. Yay, I know you're loving radians. Okay, so we're going to use these steps to evaluate a trig function for any angle. So we can find the sine, cosine, tangent of any angle in the whole entire world. Okay, mainly we're going to stick to our special ones, our multiples of 30, or our multiples of 45 degrees. We're going to stick to those specials because those are the ones we can find exactly without our calculator. Okay, so our specials are 30s and our 45s. Okay, so first we would need to find the reference angle. So a sketch may be helpful. So here I'm trying to find the tangent of negative 240 degrees. Okay, so I know tangent is going to be equal to y over x. So really what I'm trying to find is the y and x coordinate for negative 240 degrees. Okay, so I'm going to draw a sketch and figure out where is negative 240. Okay, well, that's going to be past 180. How much past 180? Okay, well, negative 240 is going to be another 60 past 180. If we take 180, 240 minus 180, we're another 60 past that. So we need to go another 60 past that. So we're going to be right here. Okay, so there's our theta, our negative 240. And then we want to find the reference angle. My reference angle would be this angle right here, and we just said, well, that's 60 past 180, so my theta prime in this case is 60 degrees. So how this is useful then is I'm able to, in this little bit right here, I'm able to create a right triangle that I know this angle here is 60. So I'm able to create a right triangle, okay, where this angle right in here is 60 degrees. So I know this one up here is going to be a 30. So I have a 30, 60, 90 triangle. So I know in my 30, 60, 90 from a couple sections ago, if the short leg is 1, okay, if the short leg is 1, then that tells me that the hypotenuse is 2 and the long leg is 1 times root 3. Okay. So what that can do is that can help me find this xy coordinate here. So we know this xy coordinate is going to be over 1 up root 3. Okay, so I know, so we want to evaluate the trig function for our theta prime, which this is our theta prime right here. Okay, so we can actually find the tangent of negative 240 by finding the tangent of 60 degrees. Okay, so we find the tangent of 60 degrees in step 3. So we know the tangent of 60 degrees is going to be, well, we can actually use at this point, we could use the SOHCAHTOA definition because we've got a right triangle. So there's my 60 degrees. It would be opposite over adjacent, so root 3 over 1. So we'd have root 3 over 1. So the tangent of 60 degrees is just root 3. Okay. But then for step 3, we need to adjust the sign depending on the location. So we know that this angle, negative 240, is in quadrant 2. What do we know about quadrant 2? In quadrant 2, x is negative. X is negative. So there my x's are negatives, my y's are positive. Which means if tangent's y over x, y is positive over negative, which means that in this quadrant, tangent's going to have to be negative. So the tangent of negative 240 is going to be negative root 3. Okay, so we just switched the sign on this guy to consider, because this was considering we're in quadrant 1, but we're not, we're in quadrant 2. So we have to adjust what we mean by sign is the positive or negative, positive or negative, positive or negative, depending on what quadrant it's in. So you're going to have to evaluate a little bit what quadrant it's in and what is that going to do to that tangent or cosine. All right, next one. All right, so now we're getting into the cosecant of 17 pi over 6. Okay, so first we need to find our reference angle. So I'm going to go ahead and draw a sketch. We know a full rotation all the way around is 2 pi, right? But 2 pi, if we're in terms of 6, we would multiply by 3, multiply by 3. So that, oh, by 6. Sorry, not 3, 6 and 6. So we know a full rotation is 2 pi, which in terms of a denominator of 6 would be 12 pi over 6. So we know all the way around is 12 pi over 6. Well, we're more than 12 pi. And if you haven't figured out already, every 90 is 3 more pi over 6s. So here we're 12. So this would give me 13, 14, 15, 16, 17. So 17 pi over 6 is going to put me way the heck over here. So 17 pi over 6 is going to put me right there. 17 pi over 6. So we need the reference angle, which is this little bitty thing right there, my theta prime. Okay, well, it looks like that is one really actually 30 degree. Okay, because if we look at, we're breaking it up into 30 pieces. So if we break a 90 degree up into 3 equal pieces, it's going to be a 30 degree, which in radians is pi over 6. And if you don't believe me, go ahead and convert. So my theta prime is going to, my reference angle is going to be pi over 6. So we would take, we're looking for the cosecant of pi over 6. Well, I could find instead the sine of pi over 6. And from that, take the reciprocal to find the cosecant. If you notice here, we're in quadrant 2. Okay. So the sine of pi over 6, again, that's a 30. It's our 30, 60, 90 idea. So I'm going to come over here and look at my 30, 60, 90. But now we're looking at the 30 degree, and we want the sine. Sine is opposite over hypotenuse, so that would be 1/2. So the sine of pi over 6 would be 1/2, because it's a 30 degree. 1/2. So then the cosecant of pi over 6 is going to be 2 over 1 equals 2 over 1. And now we're in quadrant 2. So quadrant 2, it's for sine, we're looking at the negative. We're looking at the y's for sine. If you remember from before, our sine was equal to y over r. So we're looking at the y coordinate. So the y coordinate in quadrant 2 is positive because we're up. So that tells me it would be positive. So I know then the cosecant of 17 pi over 6 is going to be positive 2. Hey, and if you're not sure, type it in your calculator to get an approximation and make sure your approximation is accurate. Okay. If you need any help, please come see me, and good luck.